Alright guys, today we are solving another optimization problem in GAMS. This time we need to decide where to install fuel stations in a city, to make sure all urban areas are covered while minimizing the installation cost. Here's the setup. The city has 5 areas, A1 to A5. We can install up to 5 possible stations, S1 to S5. Each station has a cost and covers certain areas. Our objective is to cover all areas, respect the maximum number of stations allowed per area, satisfy some logical constraints, and minimize the total cost. About the data, here is the data, so his specific station has is cost and each specific station has is covering areas, so not all stations can be installed in all the areas, but we need to respect some constraints. For example, A1, A2 and A4 can be converted by at most 2 stations. A3 and A5 can only be converted by 1 stations. Regards the logical rules, and there are 2 logical rules. The first one says that if station S1 is chosen, then either S2 or S4 must also be chosen. If station S4 is chosen, then S2 cannot be chosen. In GAMS, the first step is always defining the set, so we create set E, the areas, and set J, the station. Then we set the parameters, so we have J, installation cost for each station, and max CE, that is the maximum coverage allowed per area. Then, very important, we need to define the coverage matrix. This tells us, does station J cover area E? If yes, CPJE equals to 1. If not, CPJE equals 0. For example, S1 cover A1 and A2. The cost for the CP for S1 A1 is 1 and the CP for S1 A2 is 1. We write this as a table in GAMS. Now decision variables, xj equals 1 if we install station J, 0 otherwise, so it's a binary. Ye, count how many stations cover area E. And z is the total cost, our objective variable. The binary and the integer variable, because the number of stations cannot be decimals. They are integer numbers. About equations, we need to find the objective function. The objective function minimizes the total cost, so the sum for installing each typology of stations in the area has a cost, and if it's activated, then we activated also the cost. Coverage link for each area E, the coverage YE equals the sum of all stations that cover it. So we calculate YE with the sum of every station that is built. The coverage limit, each area must be covered at least once and not more than its maximum. So y.lower equals to 1 and y.upper equals to the max C. So these are the bounds. As last conditions, we have the logical rules. If S1 is installed, at least one of S2 or S4 must also be installed. And so we put L because it means that XS1 is influenced by XS2 plus XS4. And the last condition is another logical rule that says that if S4 is installed, then S2 cannot be installed. So one remove the other. And then we write the final parts of the writings to tell GAMS that he needs to solve the model. So we have a mod x2 whole with the indications of the specific MIP model that needs to be written. So we have x2.optci equals 0, x2.optcr equals 0, and we need to solve the name of the model using mixed integer programming, minimize zeta, mixed integer program, because we have either integer and binary. So we solve, the solver will find the cheapest set of stations that cover all areas and respect the rule. At the end, we display x.l, y.l, and z.l to find all the total results. This is a facility location problem with coverage and logical constraints, solved neatly in GAMS. Thank you for watching. See you in the next video.